Okay, one more data set for us to play around with. We'll see if we can find a formula that goes with what's given here. So this is some force. It's I don't know if it's electrical or magnetic or what, but they take different measurements at various distances from a source, and then they determine how much pull they feel at that distance. So this could be gravity. The units are a little unclear too. We'll just have to overlook that. But it's an interesting set of numbers, and I actually don't know what the formula is behind this, so we'll discover it together. So as we've seen, there's a whole bunch of different ways that these numbers could be connected, and the simplest one is just a straight line, like y equals mx. Or to use the letters that are in this problem, it would be, oops, right, keep that from happening over and over. Let me shrink that window down so I don't keep clipping it by mistake. Okay, so I said y equals mx, but using the letters that are in the problem, it would be force equals m times distance. Let's see if that holds up. And spoiler alert, it won't, but just to do this really fast, our distances go up to about 2, so we could have 0, 1, 2. I'm doing this quickly because I kind of know what's going to happen. And for the forces, our numbers tap out at 300, so we have like 100, 200, 300. And so if we plot some of these points, at 0.3, about there, we have a force of 33. At 0.2, we have a force of 75. Right off the bat, you can see we're not going to get a linear relation. This is one where as the distance gets bigger, the force gets smaller. And if we do a few more points, 0.15, we get 133. 0.1, we get 300. So it's a curve that's shaped more like this. So, not a straight line. We tried linear, didn't work. We have to try something else. Now, if we think about those curve shapes that we saw earlier, the ones for other kinds of relations, there are a couple that have this drop fast and then flatten out shape. And one of them is y equals 1 over x, what we just call a reciprocal relation or an inverse relation. That does this. And 1 over x squared also does that. The curvature is not exactly the same, but it's darn close. It's very hard to see with the naked eye the differences between these guys. So either one of those is a possibility. I'll try 1 over x, first of all, and we'll see if that linearizes this thing. And if it doesn't work, we'll try 1 over x squared. And if that doesn't work, then we'll fill the coffee mug with gin and decide what we're going to try next. So, clear some space. Alright, so I could have kept some of that. Now I have to set up the graph all over again. Oh well, I'll try to go fast. So, we tried m times plain old d. Now we're going to try, because we know it's an inverse, m times 1 over d. We'll see if we have any luck with that. So I'm making a new table of values. Instead of distance, I'm going to be doing 1 over the distance. And no change to the force. So when we're filling in this table, for each of these numbers, for each of these distances, I have to do 1 over that. On the calculator, I'll be doing 1 divided by 0.3. Or, honestly, what I'm going to be doing, I have a key on my calculator that is 1 over x. Or on some people's calculators, it's x to the minus 1. That does 1 divided by a number. So to do these, I'm actually going to do 0.3, and then I'm going to hit my 1 over x, and that'll flip it for me. It saves me a couple of key presses. It'll make this go a bit quicker. So 0.3 flip gives 3.3, and the force that goes with that is 33.3. 0.2 flipped is 5. Force that goes with that is 75. 0.15 flipped is 6.7. I'm not carrying a lot of decimal places here. I forget if I mentioned this before, because I can't draw that accurately anyway. If you tell me to draw 6.667, it's going to look pretty much the same as a 6.7 or a 6.8 because that's the limits of my drawing skill, unless I have really fine graph paper. So there's not a lot of sense in breaking your back trying to get super precise data for something you intend to graph. Two significant digits is usually about all you can manage. Let's see here, 0.1, flip that, you get 10, of course. I can do that one in my head. And the force that goes with that is 300. 0.5 flipped is 2, and 12 goes with that. 0.75 flipped is $1.33, and 5.3 goes with that. 1 flipped is 1, 3 goes with that, and 1 over 2 is 0.5, and 0.8 goes with that. Okay, let's see if we linearized it. Okay, so here I have 1 over distance, and my highest number is like a 10. So starting at 0, 1, 2, 3, that spacing's not great, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll pretend that line's more like there. That's a bit better. And for the forces, we go all the way to 300. So we have like 0, 100, 200, and 300. Let's see if we can make that work. So 3.3, 1, 2, 3, and a bit, gives us 33.3 for our force. 5 gives us 75, which is like 3/4 of the way up for our force. 6.7 is about there and gives us 133.3 for our force. Is that straight? It's straight-ish. Let's keep trying. 10 gives us 300 for our force. That's got a bit of a bend, maybe. Could be drawing error. 2 goes with 12, which is like down here. 1.33 goes with like 5.3. That's on this scale. I'm saying if that's 100, then that's 50, 40, 30, 20. That's 10, so anything lower than 10 should be even lower than that tick, meaning not very high at all. 1 goes with 3, which is down here, and 0.5 goes with 0.8, which is darn close to 0 on a scale like this. So I started out with a little hope for this line, but I mean, look at this. Down here, it's got a direction kind of like that, then it pulls up and it looks kind of like that, and near the end it climbs even faster. This thing seems to still have a curve to it. I'm not thinking that's linear. So 1 over d did not linearize it. We get to guess again. So throw away the ashes of our hopes and dreams here, and we'll make another guess. I can still use this vertical axis. I'll keep that this time. Okay. Well, 1 over distance didn't work. The other thing we said it could be is 1 over distance squared. So let's try this again. I get to blow up those. I can keep the forces. They're going to be the same every time. So now I get to do 1 over distance squared, which on the calculator I'm going to hit. I'm going to put in 0.3, hit 1 over x to flip it, and then hit x squared to square it. Flip, square, and for this I get 11.1. 0.2, flip gives 5, squared gives 25. 0.15, flip gives 6.67, squared gives 44.4. 0.1 flipped is 10, squared is 100. 0.5 flipped is 2, squared is 4. 0.75 flipped is 1.33, squared, okay, I don't know that one, 1.8. 1 flipped is 1, squared is 1. And 2 flipped is 0.5, squared is 0.25. Okay, back to the graphing pits. Let's see if we have any luck with this. Our 1 over distance squareds top out at like 100. So let's see, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And the forces haven't changed, so we can use the same vertical axis. Let's see what we get now. 11. This is 10, so 11 is just a smidge to the right. We get 33.3. 25 is right between 20 and 30 and gives us 75. 44 is like there, goes with 133, about a third of the way up. It's straight so far, but I said that last time, so don't get too excited yet. 100 goes with 300, about there. That's still looking straight. That's pretty encouraging. 4 is like there, goes with 12. 1.8 is like way over here, goes with 5.3. That's jammed in the corner so tight you can hardly see it. 1 goes with 3. All those are just going to be, I can't draw that precisely. They're all going to be in there. So, interesting. This looks an awful lot like a linearized graph. And if we're right about that, that means our formula is f is some slope that we don't know yet times 1 over d squared. All right. We tried d, didn't work. We tried 1 over d, didn't work, didn't give us a straight line. We tried 1 over d squared. We did get a straight line, and now that we have a straight line, we can talk about a slope. And slope, say it with me, is y2 minus y1 over x2 minus x1. Here's some numbers we can use on our graph, or from our table of values, sorry. If we use y2 minus y1, we get 33.3 minus 0.8. That's an 8 over 11.1 minus 0.25. Uh, 33.3 minus 0.8 is 32.5. 11.1 minus 0.25 is 10.85. And if we divide that out, 32.5 divided by 10.85, we get 2.995, which is very, very close to 3. So I think our equation here is something very close to f equals 3 times 1 over d squared. And of course you could mush that together and just say 3 over d squared if you wanted. All right. So started from this data. You graph it and hope you get a straight line. If that doesn't work, change out the d for something else. Try d squared, try d cubed, try root d, try 1 over d. We didn't do all of those, but after a couple attempts, we found 1 over d squared linearized the graph, and once it's a straight line, you can calculate this slope. A lot of physics formulae have been discovered this way, and we'll get you to rediscover a few of them for practice. Hope you have fun with it.